So we finished the last lecture with the discussion of stability of equilibria using the Koopman operator point of view. Prior to that, we also discussed how one can use Koopman eigenfunctions at eigenvalue 0 of a continuous time system to identify basins of attraction. And we're going to continue this topic of studying systems, dynamical systems that possess an equilibrium. And to start with, we're going to assume that it's stable. The condition for stability, as I said, we talked about in the last lecture. And we'll first define the notion of isostables, in this case now for nonlinear systems. That's the notion that we discussed in linear systems and linear systems before. So the situation that we start with is here, we have a basin of attraction calligraphic B, and then we have a fixed point here, and that fixed point is stable. And the key idea here is that we really like to define new coordinates inside the basin of attraction that are kind of dynamically adapted, that the dynamical system that make the dynamical system kind of the simplest in the same sense that Jordan form makes the linear system seem simple because it has a diagonal aspect to it and then off diagonal part. So we'd like to do something like that for nonlinear systems as well. We start with this concept of isostables. So we'll start again with x dot is equal to f of x. Our state space is Rn. We assume that f is a smooth vector field. We'll assume analyticity or various types of smoothness as we need it. Its flow is St, and we are going to assume that the fixed point is at 0 with this basin of attraction B. And another assumption I'm going to make is that this fixed point here has a Jacobian matrix A, which is the differential of F, the vector field itself, at 0. We are going to assume that that matrix has n distinct and non-resonant eigenvalues. If a reminder is needed, this is what we introduced when we were studying Poincaré linearization a few lectures ago. And these eigenvalues are going to be labeled by lambda j as usual. Sigma j is the real part, omega j is the imaginary part. And the stability tells us that we're going to have strictly negative, stability assumption tells us we're going to have strictly negative real parts, and they are ordered as this. So 0 is bigger than sigma 1. So this is going to be the quote unquote, lambda 1 is going to be the quote unquote slowest eigenvalue. And this is its real part. Now the isostables in linear systems we defined as the level sets of the slowest eigenfunction phi1. So what we did in linear systems is something that we would like to repeat here in the nonlinear systems case. And in particular, we're going to be interested how the level sets of, again, the slowest eigenfunction provide us with contours such that the dynamics flows from one of those contours to another, and as we converge to the fixed point, has in some sense well-defined limiting behavior, the limiting behavior being determined, as we are going to see, by this matrix A. So this is the idea. So in the linear case, we took the slowest eigenfunction phi1 and we looked at its level sets and called those isostables. We're going to do something very similar here. We're going to use the fact that under the non-resonancy condition, we have a nice analytic conjugacy in the basin of attraction. And phi1 is the eigenvalue of the associated linear system associated to our nonlinear system by conjugacy. So that linear system is going to be driven by this matrix A. And phi1 composed with H, where H is the conjugacy, is the eigenfunction S1. And then we're going to be defining isostables as the level sets of the absolute value of the eigenfunction S1. And we've seen that type of a definition before in linear systems. We write S1 in its polar form as R of x e to the I theta x. Theta is the argument. And therefore, the norm of S1 is precisely R here. So that's the setting for finding isostables for nonlinear systems. And now we're going to show that the asymptotic evolution of the flow is dominated by a term associated with lambda 1. So as I mentioned, the isostables, those nested level sets, are special because they will be shown to have a very specific approach to a fixed point that is consistent with the linear dynamics close to the fixed point. So let's do this formally. If we have real lambda 1, let's start from the conjugacy relationship. We expand around the equilibrium 0. So the conjugacy relationship says HST is EATH. So we take H on the other side. That's H inverse EATH. And so now we can replace this part here with a spectral expansion, right? This part here is driven by linear evolution. So if we look back to our spectral theory on linear equations, we'll find that e to the ATH is really sum j is equal 1 to n. This is the dimension of our state space, e to the lambda jt, phi j of h of x. So that's the only little twist, because here we have h of x that e to the at is acting on, not x itself. So the argument of the linear eigenfunction phi j, remember that's the inner product of x and wj, is the argument is h of x. And then we have vj, that would be the eigenvector, jth eigenvector of the matrix A. So now we know that h of 0 is 0. The fixed point at the origin maps to a fixed point at the origin by conjugacy. And so H inverse of this argument here, evaluated at 0, of course, when t goes to infinity, this is 0, gives us precisely 0. The H inverse maps 0 to 0 as well. And so the first term in the Taylor expansion in terms of phi j's here is dH inverse at 0 applied to this same argument here. And then the remainder is of the order phi j squared because we assumed analyticity in terms of phi j here. So recall phi j's, the eigenfunctions, are 0 at 0, provided lambda j has a non-zero real part. So also because they're smooth, close to the origin, they have small values. And so this is the Taylor expansion in terms of phi j. So we get order phi j squared over here. And this is approximately equal, so for phi 1 small, to e to the lambda 1 t phi 1 h of x v1. So as I said, the flow itself, st, is dominated by the contribution associated with lambda 1 when t is large. So in the asymptotics, when t goes to infinity, this term here dominates. This is S1, it's phi 1 conjugated to h, v1. So this is the kind of the first term in the expansion when t is very large, or equivalently when x is very small. So now we've shown before, this is very, very similar to the argument that we had in linear systems. We've shown before that the points characterized by same value of the absolute value of S1 are initial conditions of trajectories that converge synchronously to the fixed point. So they converge to the fixed point synchronously according to this expression. So they pass from one level set of S1 to another level set of S1. And now we'll repeat similar calculations like in the linear case. We are going to, in the case of a real eigenvalue, replace the absolute value of S1 with e to the lambda 1 tau of x. And then we have that st of x is equal to v1 plus minus e to the lambda 1 t plus tau. Now, if lambda 1 is complex, then we are going to define e to the sigma 1 tau to be 2 S1x absolute value. So absolute value of S1 of x. And theta of x is the angle. And so we get the approximate evolution of ST to be the real part of V1 e to the I omega 1 t plus theta e to the sigma 1 t plus tau, right? So that is really coming from this expression here as soon as we replace S1 with the appropriate expression, exponential expression. All right. So it's pretty easy to see that it is an equivalent and general definition of isostables. So the definition that we gave initially is that the absolute value of the slowest eigenfunction S1, the level sets of that are isostables. And so now we're going to define the isostable I tau as follows. That's the set of all points x in the Bayesian attraction such that there's a theta in this set capital theta that is either 0 pi. So this could be the case when lambda is real, lambda 1 is real, because we have a positive and a negative version of the eigenvector, or the set theta is 0 to pi if lambda 1 is not real. It's actually complex, and in that case we have the oscillatory terms in here. And so we need to find a theta in this definition such that the limit when t goes to infinity, e to the minus sigma 1 t, absolute value of st, the flow, minus 1/2 of the contribution to evolution of the slowest eigenfunction and the slowest eigenvalue. That's this part here. And the reason why 1/2 is here, that when we take the real part, we get twice the contribution, once from this term, once from that term. So we're requiring that when we multiply this absolute value of the difference between ST and basically the linear, slowest part of the linear evolution. So when we multiply that with e to the minus sigma 1, sigma 1 is the real part of the slowest eigenvalue. So this would be positive because sigma 1 is negative, that the limit when t goes to infinity is equal to 0. So all x that would satisfy that condition with that particular theta would be on one isostable, and it's pretty easy to see that that's consistent with what we've done before, because this e to the sigma 1 tau is really related to the level set of the slowest Koopman eigenfunction, as is this term over here. That's the complex conjugate of this whole term over there. So obviously, if you have 2 points that have exactly the same value of the Koopman eigenfunction, then they would satisfy this in exactly the same way, and the other way around. So as I've drawn before, what this means is that the basin of attraction of the fixed point is foliated or partitioned into isostable leaves. So again, we get an invariant partition of the type that I've drawn before, that the dynamics just kind of squishes down into the fixed point. Except in the case of multiple eigenvalues, in that case, V1 might not be unique. The isostables are uniquely defined through this definition. So now that we have the definition of isostables, let's go back and look at where we are so far. So we have the basin of attraction, B, and then we have a fixed point, and let's say that's a stable fixed point. So everything converges to that fixed point from the basin of attraction. And now, so far, we have this definition of isostables. These are these level sets of the slowest eigenfunction. I'm drawing a couple of those here. But if I would have another set of level sets, let's say something like this, then I would actually have a set of coordinates. So the value of the level sets that are drawn in red would be one number, and then the ones that are drawn in green would be another number. Then I would have a set of coordinates in this basin of attraction that would kind of be dynamically adapted and would put the system in a simple form. And indeed, we wrote the eigenfunction S1, the slowest eigenfunction, in terms of its modulus and the phase, so R1 and theta 1. And if we do the following calculation, so S1 dot is R1 dot e to the I theta 1. So remember, S1 is R1 e to the theta 1. So if we have S1 dot is R1 dot e to the I theta 1 plus R1 I theta 1 dot e to the I theta 1, R1 dot and theta 1 dot is what we'd like to determine, but that's also equal to, of course, lambda 1, which is this, times S1, which is this. So this part I obtained by pure differentiation, this part I obtained by definition by the fact that S1 is actually an eigenfunction, so S1 dot is lambda S1. So let's now compare the terms. First of all, this cancels everywhere. And then I have R1 dot to be equal to sigma 1 R1. That's the part that is real. And then theta 1 dot, here is I, and that's I as well. So theta 1 dot is omega 1. And it's a very nice set of equations that we came by in the linear case when we introduced the quote unquote polar coordinates that depended, that were obtained the same way from the slowest Koopman eigenfunction as I have now. And so this gets us to a very simple set of equations that we can, or simple set of equations for the evolution that we can call equation in radial coordinate and the angle coordinate. And so now theta 1, which is the argument of e to the I theta 1, that's in the definition of S1. So the level sets of theta 1, remember theta 1 is a function of x, give us these angle coordinates and achieve that a goal that I just gave in 2D. These are enough to describe every point in the basin of attraction. And so we put the system in a really, really simple form by what actually is a conjugacy from the original system x dot is equal to f of x to this system here. That is very simple and obviously immediately solvable. So as in the linear systems, these eigenfunctions in the nonlinear case provide us with the ability to put the system in quote unquote the simplest form possible. So now we're going to expand our discussion to systems that have, besides stable directions, also unstable and center directions. And so in the case when we have a fixed point that has unstable and center directions, so let's draw something like that. So for example, in 3D, we could have a two-dimensional stable direction and then maybe a one-dimensional unstable direction. One of the most important things to know about in such a case is the invariant manifolds associated with the stable, unstable, and center motion. Now, in linear systems, we had stable, unstable, and center subspaces. In nonlinear systems, we have stable, unstable, and center manifolds. So just as a reminder, an invariant manifold is the set of all x in the state space such that starting from the initial condition x, the flow in positive and negative time stays in M, right? So that's the definition of invariant manifold. And so it is the proposition that's going to tell us something about detecting invariant manifolds. So if we have a nonlinear system, x dot is equal to f of x, with this flow st, and our state space M is a manifold of dimension little m, and let S, this boldface S, be a collection of Koopman operator eigenfunctions, and let there be k of them. And let's assume that they are smooth, and they can be generalized eigenfunctions. They don't necessarily need to be pure eigenfunctions. So if we consider the zero level set, ZS, of this, so it's a joint level set of all these functions, and we assume that ds is a full rank on that zero level set, then that level set is an m minus k dimensional invariant manifold for the flow. It's a nice little result. It follows directly from differential geometry. The first statement that we need to make if we want to prove this is, first of all, the functions S satisfy S dot is JS, where J is the Jordan 4 matrix. That's just by the property of generalized eigenvalues and eigenfunctions and generalized eigenfunctions. They always satisfy the vector of generalized eigenfunctions always satisfies this equation. And so if S of x is equal to 0 initially, then S of STX is equal to 0 for all time t. So therefore, if you start on a zero level set, you stay on a zero level set. So the joint zero level set of these eigenfunctions is in fact an invariant set. Now, the fact that it's a manifold of dimension m minus k, that's a standard theorem in differential topology that says that if you have k of those functions, then they're joint zero level sets of functions that are independent in the sense that ds is of full rank. Cuts out, so set of k such independent functions in an m-dimensional space cuts out the manifold dimension m minus k. So for example, if one has the equation for x squared plus y squared is equal to minus 1 is equal to 0 in a plane that defines a one-dimensional manifold, which is a circle of radius 1. That's the same theorem. The same theorem verifies that, as it verifies that some general set of C1 functions, the associated invariant set is going to be a manifold of dimension m minus k. So that's nice. Now we know that zero level sets cut out m minus k, zero level sets of k smooth Koopman eigenfunctions cut out manifolds of dimension m minus k. Some of the most important invariant manifolds are the so-called stable, so we label it here as WS, and unstable, label as WU, manifolds of an equilibrium x is equal to x star. And these are defined globally in state space with asymptotics. So WS be in the location of all x in a state space such that the limit when time goes to infinity, STX, is x star. WU is the set of all x such that the limit when t goes to minus infinity, STX is equal to x star being the equilibrium here. And the center manifold is really defined locally in a small neighborhood of the origin as an invariant manifold which is tangent to the center subspace. So let me draw a figure here, maybe in 2D. Let's say that we have a system whose linearization is such that we have a one-dimensional unstable subspace and then a one-dimensional center subspace, and the center subspace is really obtained as a line of fixed points in this particular example. So our unstable subspace would be EU here, and then the center subspace would be this one, EC. And then the center manifold theorem tells us that the center manifold exists locally around this equilibrium here at 0. And it's obtained as a graph over the center subspace. So that graph, that function that we define here as G, let me draw this a little bit better. So this would be the center subspace, and then we would have the center manifold, and this graph G that I defined over here is a graph over the center dimension, but all of this, the existence of this manifold here and the associated unstable manifold, of course, is all defined globally, locally in the neighborhood of this origin. And so one of the topics today is going to be, or in this lecture, is going to be how do we extend this globally. And as we will see, one of the consequences of this is that the definition of the center manifold can become, in fact, global and unique. So that's where we're going with this. And let's continue here with the analysis. So we're going to set x star, our equilibrium point, at 0 again. Nonlinear system is now going to be labeled z dot is f of z because I have x and y is reserved for some other representation. Eigenvalues at the fixed point 0 are lambda j. S, C, and U are the number of negative real part eigenvalues, 0 and positive eigenvalues of the matrix DF. And lambda 1 to lambda U are positive. Real part eigenvalues, lambda U plus 1, lambda U plus C are 0 real part eigenvalues. And lambda U plus C plus 1 to lambda U plus C plus S, that's the number of stable eigenvalues, are negative real part eigenvalues of DF at 0. And then we're going to split this DF at 0 into 0 real part eigenvalue block B. That's going to be a C by C matrix. That's the number of 0 real part eigenvalues. And a non-zero real part eigenvalue block A, which is U plus S cross U plus S matrix. And so Palmer provided us with this linearization theorem that generalizes the Hartman-Grobman theorem, or Hartman-Grobman linearization that we discussed before. And it tells us that this equation here that we started from, using the blocks A and B of the matrix DF of 0, can be written as x dot is bx plus g. This is some nonlinear function of x and y. And y dot is ay plus h of x and y. And we are going to request that h and g would be bounded and Lifshitz with sufficiently small Lifshitz constant. This basically ensures us that g and f don't grow faster than linearly at infinity. That's the basic idea of these conditions. And then Palmer proves that this sort of equations is C0 conjugate to this system. X tilde dot is B x tilde plus G tilde x tilde. So that's really a variation of this with the same matrix B, but maybe different observables x tilde. And then Y tilde dot is A Y tilde. So that removes the H part from this equation here. And G tilde is a bounded and Lifshitz function, so it satisfies something similar to this. And so this is interesting because if we go back to our linear system analysis, we're going to almost immediately see that this will yield us with Koopman operator eigenfunctions for this system. And so then we find that the following is true. So the system that we just described has U unstable generalized eigenfunctions, S1 to SU, and S stable generalized eigenfunctions, SU plus 1 to SU plus S of the Koopman operator. And the joint zero level set of the unstable generalized eigenfunctions is the so-called center stable manifold. So it contains the center directions and the stable directions. This LC, the joint zero level set of stable and unstable eigenfunctions, is the global and unique center manifold in this case, WC, and LCU is the center unstable manifold CU. So this uniqueness here is really due to our definition, and I'll give an example of that in a moment. So this is proven as follows. Palmer has shown that this equation is valid for these functions y tilde of x and y. X and y are our original variables. And now let's have the matrix V, a matrix that transforms A to its Jordan form J. And now we define S, a new set of functions or observables, to be V inverse y tilde. Then we will have that S, which is a set of stable and unstable eigenfunctions, satisfy the equation S dot is equal to JS, right? Because we're just diagonalizing this system and we're finding new coordinates. And if you remember our lectures on linear systems, we can define new coordinates such that in those coordinates, the equation is described by a Jordan normal form of J or driven by Jordan normal form J. And so S, this set of variables that's obtained by Palmer's Y tilde, is in fact a set of generalized eigenfunctions of the Koopman operator. Now, the joint zero-level set of these is the center manifold, and we know the dynamics on it. And that dynamics is x tilde dot is b x tilde plus g tilde x tilde. So that much about the center manifold. Now, let's take the situation in which we set all the unstable eigenvalues to 0. Then we are going to obtain a set that is a center stable manifold on which the dynamics is driven in part by the center equations and in part by the stable equations, of course, analogously for LUS for the center unstable manifold. So that gives us a nice global description of the types of systems, nonlinear systems with equilibrium. In this case, the equilibrium does not have to be a stable equilibrium. It can have unstable and center directions. And we see that the key invariant manifolds, the center manifold, the center stable, and the center unstable manifold are obtained as zero-level sets of Koopman eigenfunctions. And that's really the main message of this theorem. So I mentioned that we're going to talk about an example in which non-uniqueness is obtained. So this is the famous example by Kelly of a vector field with non-unique local center manifold. I think Kelly might have actually considered a stable direction here, but that is a non-essential difference. So x1 dot is x1 squared and x2 dot is x2. The state space portrait looks like this. So the unstable direction is obtained as the x2 axis, right? x2 dot is x2 is exactly this. And then the center direction, this x1 part has just a nonlinear term. So its linearization is really x1 dot is equal to 0. So in the linear case, we would have this whole x2 is equal to 0 axis filled with fixed points. And so the question is now, what is the center manifold? And in the local theory, we'd say, well, any one of these curves here that take off as being tangent to x2 is equal to 0 at the origin, any of these curves satisfies, or rather is produced by the local center manifold theorem, including this one. All of these curves given by x2 is a e to the -1 over x1 for x1 bigger than 0. All of these curves, when joined with this x2 is equal to 0 for x1 less than 0, all of them give you local center manifolds. But there is only one of those that is such that on the associated manifold, there is no exponential part of the evolution. Namely, for any of these manifolds here, the motion in the x2 direction is exponential. x2 dot is x2. The only one that doesn't have that property is really the former stable subspace. Now, the Koopman operator-based theory says that's the global center subspace, and it uniquely satisfies the condition on that global center subspace because it doesn't have any exponential part of evolution on it. And so the Koopman eigenfunction x2, note x2 dot is x2. So that satisfies the condition for x2 being a Koopman eigenfunction with eigenvalue 1, happens to be unstable. x2 is equal to 0 is precisely this line that is in this theory, the global center manifold. And that concludes our our discussion of fixed points or properties of Koopman operator, and also discussion of properties of motion in systems with such fixed points, in the case when the fixed point itself has unstable, stable, and possibly center directions, so we don't have a basin of attraction, and still the invariant manifolds can be determined by setting or considering zero-level sets of the associated Koopman Eigen Functions. So we've discussed the geometrical properties so far in terms of specific eigenfunctions of the Koopman operator. The basins of attraction were determined by properties of Koopman eigenfunctions at eigenvalue 0. The stability was really associated with the properties of Koopman spectrum or Koopman eigenfunctions, eigenvalue with the real part, well, in particular the real part of the eigenvalue. So if the real part of the eigenvalues was less than 0 for those principal eigenfunctions that are compositions of the linear eigenfunctions with a diffeomorphism, then that would lead to a stable system. And then zero-level sets of stable, unstable, and center eigenfunctions were shown to produce invariant manifolds of centers, unstable and stable type. Now, the final topic in this discussion of systems with equilibria, nonlinear systems with equilibria, is the notion of the spectral expansions. And I would like to obtain, just like in the linear case, a spectral expansion that determines the evolution of any observable that we choose on the state space. And the way we are going to do this is starting from the assumption that we have non-resonance conditions at 0 at our fixed point, and the fact that V is analytic. We're going to do, again, the change of variables. The Koopman eigenfunctions themselves can serve as coordinates for a nonlinear system. I've just shown that on the example of isostables. As long as the change of variables from x, our original variables, to y, which is s of x being the n Koopman eigenfunctions, is one-to-one and smoothly invertible. So let's assume that exists, and let yj to be just sj of x, where sj is an eigenfunction of the Koopman operator. We will have yj dot is lambda j yj for each of these, right? And under our assumptions, we can invoke the Poincaré theorem and the global linearization, and this transformation here would be analytic. So now we'd like to find an expansion of an arbitrary observable into eigenfunctions of the Koopman operator. So if such an observable f is analytic, let's perform the Taylor expansion of f, whose argument now we are going to take to be S inverse of y. So look at the change of variables here. Y is S of x, so x is S inverse of y. So we're going to do an expansion in terms of f of x, but we're going to replace x with S inverse of y. So f of S inverse of y is f of 0, because that's if the equilibrium is at y is equal to 0, or equivalently at x is equal to 0 for the linear and nonlinear version of this system. And then we have the differential of f acting on ds minus 1. So this is just chain rule differentiation of this, multiplying y. So everything here is evaluated at 0 at the equilibrium. And then we have these terms according to multi-variable Taylor expansion that contain ds inverse, the Hessian matrix of f, which contains second derivatives of f with respect to x. And here is the first derivative multiplying the Hessian the Hessian matrix that takes the second derivative of SK inverse, that's the component, kth component of this S inverse with respect to Y coordinates. So that's a multivariable a Taylor expansion of F. And so now we know that Y is S1 to Sn, and let's actually do a little more general discussion and expand for a vector valued observable F. So for a vector valued observable F, we are going to have an expansion, a Taylor expansion that looks something like this. We have these Koopman Eigen functions on various powers, K1 to Kn. We sum over all these powers, and the coefficient, B tilde, which is a vector coefficient, is going to be indexed by K1 to Kn. And these things here we call Koopman modes. They're the coefficients of expansion into, in this case, polynomials in eigenfunctions. Okay, so up to linear terms, let's consider these Koopman modes now. Remember, this is a fully nonlinear expansion. We have an infinite number of modes here, but the first one, if you look back, this was the scalar case, but equivalently in the vector case would be just boldface F at 0. And that boldface F at 0 is precisely V bar, where these coefficients K1 to Kn are just 0. That's the first order coefficient. And that indeed is, if you remember from before, that's the value of F at 0, which is also the time average of F that the system is seeing. Now, V bar, the first Koopman mode, if we put just one at the jth position here, then we obtain partial F with respect to xk at 0, partial sk inverse with respect to yj. That on scalar case, you can see up here. So that's the Koopman mode, the order 1 Koopman mode. There is, of course, many of them, right? Because these coefficients K1 to Kn, there is n of them, and they're elements of integers and integer space Nn, or integer lattice. But you'll notice that these are composed of first derivatives of the observable itself and first derivatives of the inverse transformation provided by Koopman eigenfunctions. We can continue working out these, and if we have, for example, the second order modes are going to be combinations of second derivatives and first derivatives of the observable and the diffeomorphism itself that we have used, the change of variables we have used. So now, to simplify a little bit, let's say that our observation is precisely the state. And in that case, it simplifies. So these Vk1 to Kn, the Koopman modes, are obtained by this expression. We still have this S minus 1 over here, but the reason by partial F with respect to X doesn't show up, it did show up here, is that it's identity, right? Because we are observing precisely X. So the derivative of F with respect to X is identity. So that one is just identity. The second part here stays. And the eigenvalues of, in particular the eigenvectors of df in particular correspond to partial S inverse with respect to yj at 0. So we have ds inverse to be equal to V, where the columns of V are actually the eigenvectors Vj. And so if we also differentiate y, which we can write as S inverse S of y, and then use the chain rule, we get delta ij, which is precisely that. So this is the identity matrix, right? This is really the identity. is dsi at 0, and this is just Vj. Yep. So the gradient or the differential of Si, which remember is the ith Koopman eigenfunction, must be the left eigenvector, because this is identity and this is the eigenvector of df. Yeah. So therefore, dsi, when multiplied with Vj, gives you identity. That means the dsi must be precisely the left eigenvector. That's the property of the dual eigenvectors of df. And now, if we expand the Koopman eigenfunction into its linear and higher order components, we get dsic at 0x plus this small order in terms of x. And that's really xwi, because this thing here turns into wi. And so we are seeing that the Koopman eigenfunctions are in fact the linear eigenfunctions plus some small order in terms of size of x for x small, right? So that's the place where you can perform the Taylor expansion or utilize the Taylor theorem, and therefore these nonlinear eigenfunctions are well approximated by the eigenfunctions of the linear system close to an equilibrium. Go a little bit further, and so now that we have f of x here expanded in terms of Koopman modes and Koopman eigenfunctions, we can apply the Koopman operator to f. And of course, it only acts, the rest of the stuff here is the modes themselves are constants. They're constant vectors. So it applies to eigenfunctions by taking another eigenfunction on power k1, that is e to the lambda 1t times k1. So when you apply the Koopman operator to an observable f, it really produces a sum of this form, where again, just like we had on nonlinear observations on linear systems, the eigenvalues associated with it in the spectral expansion are integer combinations of the first n eigenvalues, or the eigenvalues of the linearization. And so again, for a nonlinear system, knowing a finite number of eigenvalues and working in the analytic category, we know them all. And so therefore it ends up being a finite calculation. The same for eigenfunctions. Once we determine n eigenfunctions, we know them all, because we just need to utilize the integer powers of these. Remember, the algebra says, algebraic properties say that if you have an eigenfunction, you multiply it with another one, then you get another eigenfunctions. The only thing that we really need to determine beyond these basic n ones are the Koopman modes themselves. But as I pointed out before, a few of them we already know. One of them is the time average mode. One of them is the eigenvector mode. And then we have these additional quote unquote nonlinear modes that also participate in this expansion. And so if we take the observable f of x is equal to x, then this turns into this expression here, where we have utilized the fact that now we get eigenvectors as the first set of modes, the eigenvectors of the linearization, and then we have split up any of the higher contribution modes, higher in terms of the fact that they're combinations of these eigenvalues lambda j that are associated with linearization, and that resembles quite a bit the linear expansion that we had. The linear expansion, on the other hand, had only n terms. The nonlinear one contains an infinity of terms, but those are put together by products of Koopman eigenfunctions and these integer combinations of Koopman eigenvalues that I call a lattice of eigenvalues over here. Okay. So this is quite an interesting realization here. When we worked with linear functions and linear systems, the only thing that we needed to consider in the expansion of these n terms, when we are in the nonlinear context, on the other hand, the only thing that changed is that now in principle, we have an infinite number of terms. But this is really like if one is doing a Fourier analysis and one is looking at a sinusoid, that there is only one frequency. When one looks at the square wave, of course, we have an infinity of frequencies, but they're all related to each other. Omega, 2 omega, 3 omega, where omega is the base frequency. Very similar here. If we find lambda 1, lambda 2 to lambda n are additional eigenvalues that we need to consider for the nonlinear part are k1 lambda 1 plus k2 lambda 2 plus kn lambda n over all the possible combinations of integers. So in that sense, the linear and nonlinear case are somewhat on the same footing. We also have a spectral expansion in the nonlinear case is just infinite. And so, of course, what is helpful if we have these terms here, where lambda 1 to lambda n have negative real parts, then many of them are going to decay very fast. And so very often they can be dismissed in the analysis. So the Koopman eigenfunctions in the nonlinear case are nonlinear. In the linear case, they are linear. The expansion itself is asymptotic in nature, namely, it really depends on the objects, eigenvalues, and eigenfunctions that are determined in some sense by the singularity itself, by the fixed point. So that's an important property. So how did we get there? There is some work that was written in a paper by Yuheng Lan and myself that uses local linearization theorems and then makes them global. The notion of isostables was proposed in a paper by Alex Mohoa and myself and Jeff Mollis. And then the stability theory was Alex's work as well. So he and I wrote a paper on this back in 2013. And that's where these types of analysis originated from. So some of the references here, and these global stabilities first appeared in IEEE, in CDC conference, then later on in IEEE transactions. And then, let's see, the paper on isostables is this one. And the spectral expansion was also written down in a number of these papers that I just mentioned. So that ends our discussion of systems with equilibria, and we'll continue next time with the topics in numerical analysis.